When polymerization occurs via condensation reaction, we call it condensation polymerization. Usually, there are two types of monomers react to give condensation polymers. The main difference between a condensation polymer and an addition polymer is the removal of small molecule when a condensation polymer occurs. Whereas in addition polymers, all the monomers combine to give only one product. There are two types of condensation polymers we need to learn in our syllabus. We will be learning one or two extra. The first type is polyester. We will see how a polyester forms. Dicarboxylic acid molecules can react with diol molecules in the presence of concentrated sulfuric acid as a catalyst to form polyesters. First of all, what is a dicarboxylic acid molecule? It is a molecule with two carboxylic groups. What is a diol molecule? It is a molecule with two alcohol groups. We learned in the esterification, a carboxylic acid can react with an alcohol to give an ester. So the same reaction is going to occur. Let me show you how the bond formation occurs. The carbon atom at one end of the carboxylic acid will combine with the oxygen atom at one end of the adjacent alcohol molecule to form an ester bond. Here is the ester linkage. This is the ester linkage. Now we have another carboxylic group at the other end of the carboxylic acid, so it can react further from this end. Similarly, the other end of the adjacent alcohol molecule has more alcohol group, one more alcohol group, which can bind to another carboxylic acid via similar reaction. So this continues with thousands of molecules giving you condensation polymer. This polymer is called polyester. Why? We have ester linkage repeated many times in the molecule. Carefully see, at the end of the two corners of each box, here we have the same groups, and the other one is the same alcohol oxygen atoms, and the other molecule has the same carbon oxygen double bond. So this happens again and again. Now let's figure out what is the repeating unit of this structure. Unlike in addition polymers, in condensation polymer, the repeating unit is going to be larger because it should contain the parts of both monomers. Now let's start from this end and we'll see where we find the same thing again after the two monomers added. So when we search through this, we can see, we can find this is, or we can find this as the repeating unit. So let me show you how to write the balanced chemical equation for the polymerization. Here we have the repeating unit of a polyester. The part from the dicarboxylic acid and a part from the alcohol. And here we have the ester linkage. So when n number of dicarboxylic acid reacts with n number of diol, we will get n times of this polyester repeating unit. We can also write 2n types of water, and this represents the balance equation for the formation of polyester. We'll move on to an example of a polyester. This is how we write the repeating unit. First, the part came from the dicarboxylic acid. You know the two OH groups have been removed. And the part came from the alcohol. You know that the hydrogen atoms have been removed. So this is your repeating unit. And you know, according to this, we can write 2n monomolecules have been produced also. So the polyester you obtain here is well known in our day-to-day use. This is called terylene. Terylene is used for the shirts and the other clothes and also for bed linen. And it's woven with cotton. The resulting fabric is more hard-wearing than cotton and doesn't crease easily. Terylene is also sold as a polyester threads. Let me give you another example for you to practice. One important thing to remember, you don't have to remember these structures and the names of the carboxylic acids and these alcohols. You just have to remember the dicarboxylic acid and the diol with that box notation. Yet, you should be able to figure out whether it's a polyester or not by looking at a real structure. So let's move on. Here are the two monomer molecules. A dicarboxylic acid with 6 carbon atoms and a diol also with 6 carbon atoms. So forget about these middle parts of these two structures. Just have to focus on the formation of the ester link. Here we have the OH and H reacting, and OH from this end and H from the other end. So let's try to write the rest of the molecule. So what you have to remember here, the carbon-oxygen double bond from the carboxylic acid, when you start from that end, you will end with the carbon-oxygen single bond of the alcohol. Vice versa. So this is the answer for the example I gave you. Do we always need a dicarboxylic acid and a diol in order to form polyester? The answer is no. You can do it with a molecule which contains both the functional groups attached. You can see this molecule has COOH group as well as the alcohol group or the OH group. So now, between the same type of molecule, the formation of polyester can happen. Why? The carboxylic group can react with the alcohol group of the adjacent molecule, and the remaining carboxylic group of that adjacent molecule can further react to form the polyester. So if I write the resultant molecule, it's going to be a macromolecule again. But the repeating unit of the previous polyesters we drew and the one that we have just drawn are slightly different. However, in this repeating unit, you have the O at the one end and the CO at the other end. Whereas this is how the repeating unit of the previous polyesters look like. You can see around this box you have C double bond O groups, two groups of them, and two oxygen atoms around this box. But in this case, around the box you have one oxygen with single bonded, one oxygen single bonded, and the other side you have carbon oxygen double bond attached. So you can clearly see this part is going to be its repeating unit. Now we can write the balance equation for the formation of polyester with one type of monomer like this. Here we have the monomer molecule, the removal of H and the removal of OH. And I write this oxygen atom, and I write this oxygen atom without hydrogen, and we have the box, and C double bonded O and the OH is removed. Now I can draw the bracket and putting n times, and I get n number of water molecules. So we learn polyesters starting from dicarboxylic acid, diols, and also polyesters from one type of monomer. We learn terylene as the main example for polyesters and its uses. Polyamides. Dicarboxylic acids react with diamines to produce polyamides. Let's learn this reaction. Here is the dicarboxylic acid as we learned earlier, and here is a diamine molecule. What is a diamine molecule? It is a molecule with nitrogen atoms attached. There is an amine group. It has nitrogen and two hydrogen atoms. Why does nitrogen have two hydrogen atoms? Nitrogen's valency is 3 because it has 5 outer shell electrons. Therefore, it needs 3 more electrons to fill these 3 positions, so then it can get the octet completed. Therefore, nitrogen forms 3 covalent bonds if they are single bonds. When nitrogen binds to the carbon skeleton from single bond, obviously it needs to have 2 hydrogen atoms. So this is the new molecule you are going to learn, diamine molecule. So here we have the usual one, dicarboxylic acid. Dicarboxylic acid. Similar to the polyester formation, in polyamide formation also we get a condensation reaction taking place. A water molecule is removed in this way. You can see hydrogen from nitrogen and the OH from the carboxylic acid is removed. This side also the OH from the carboxylic acid removed and H from the nitrogen removed. Let's see your final product. You get carbon oxygen double bond and the carbon oxygen double bond again. Now we get nitrogen and one hydrogen still attached, and from the other end we again get nitrogen bonded to another dicarboxylic acid. So this will give you a new linkage called amide linkage. This is amide linkage. So the whole thing that you have prepared now is called polyamide. We call it polyamide. This amide linkage can be also called as a peptide linkage. Which is a bond found in proteins. Polyamides can also be called polypeptides when we consider the linkage as a peptide linkage. There is a small difference between the polyamide I have drawn here and a protein that will be discussed in the video which is under the topic of biomolecules. Here is a real example of polyamide. We react hexane dioic acid with hexane 1,6-diamine. What is meant by hexane dioic acid? 6 carbon atoms and it has 2 carboxylic groups. We just learned what is an amine, what is a diamine. So hexane 1,6-diamine means you have 2 amino groups at the 2 corner carbon atoms. I emphasize again, you don't have to remember these names and structures, but we should be able to figure out whether it's a polyamide formation. Let's draw the repeating unit. You don't have OH group this time because it's removed. You have carbon-oxygen double bond, and here is the core of the molecule, and again carbon-oxygen double bond. Now the amide bond is produced. So you have CH2 6 times and NH, and H from that side is also removed. So here is the repeating unit, and at into n times we can call it the polyamide. And this polyamide is well known as nylon, and this is specifically nylon 6,6, which means the 2 monomers have 6 carbon atoms each. So let's have a look at it again. You have hexane dioic acid, hexane diamine forming nylon and producing obviously 2 N1 molecules, and with N amount of each monomer. Nylon is one of the most used polyamides in our day-to-day life. It can be drawn into tough, strong fibers that do not rot away. So, it is used for threads, ropes, fishing nets, cables, car seats and carpets. Here is an example for you to try. A special carboxylic acid, another special diamine are going to react. Pause this video and have 1 or 2 minutes. Pause this video, take 2 or 3 minutes and try the structure and come back to the video. Let's see whether your answer is correct. So you take this OH group of one end of the carboxylic acid, and the H of the amine group will be removed, and H from this side and OH from this side will be removed. So you get carbon-oxygen double bond, C6H4, carbon-oxygen double bond, NH, C6H4 and NH again. Here we have the amide link. So this is going to be the repeating unit, and 2 N1 molecules, and n number of this and n number of this. This example is also an actual polymer, which is polyamide. We call it Kevlar. And also similar structure could be found in another polyamide called Nomex. Kevlar is well known for making bulletproof jackets. Do we need 2 different monomers to form polyamide? The answer is no. Likewise in esters, we learn you can do it in one type of monomer. Here we have a molecule which has the COOH group and also NH2 group. And when we react this molecule with another molecule or with many of these molecules, you can have the polyamide produced. The OH group of the carboxylic group and the H from the NH2 will be removed, and that will continue from the other two sides also and giving you a macromolecule. Here we have the part of the polymer produced like this. If you observe carefully, you can see this is its repeating unit, which doesn't have two monomer units combined. Here we write the reaction with one monomer molecule and one repeating unit. So you can form polyamides with one type of monomer as well. This is what you find in the formation of proteins, because this monomer molecule has an amino group and also an acid group. So you call it amino acids. So these amino acids combine to form a polyamide, or you call it polypeptide, which is the primary structure of a protein strand. So this is your protein.